So if X is a point, then its nth homology group is 0, and the only non-trivial homology group it has is in dimension 0. So Hn of X is 0 for all n greater than 0, and it is in 0th dimension. H0x is ring of integers. Now this is extremely important, because when we talk about reduced homology group, what we want is that a space which is equivalent to point should have 0 homology groups in all dimensions. So we will slightly modify what we are writing here in a bit. So what is the proof? The proof is very simple. There is a simple, like a unique singular n simplex sigma n for each n. So if it was simplical complex, we would have just written a point in C0 and put zeros everywhere, and it would have been clear. But here we have maps acting on the space. So we have this maps in all dimensions. So see that there is slightly more complexity here, but that complexity is not much, as we will see. Yeah, notice that in simplical complex we would have very easy, we would have just put single integers. Yeah, so what is you just apply the boundary to it. So before we proceed any further, just apply the boundary to it. So this simplex sigma n minus 1 is unique. Yeah, let me color it. Why I am coloring it? Because I want to, since this is unique, it can come out in the front. And what we get is, these are n plus 1 terms. Yeah, you can see why. It goes from 0 to n. So 0 to n, 0, 1, 2, 3, 4 to n is n plus 1. So this is 0 for n odd, because n plus 1 is even number of terms will cancel out, minus 1 plus 1. And for n even, n plus 1 is odd, so you just get sigma n minus 1. So this is how the complex is going to look like. Yeah, there's a unique singular n simplex in every dimension. Now again I will say, we would have, if this was simplical complex, you would just put a ring of integers in C0 and 0 everywhere else. But since it's singular, we are putting ring of integers. So what should we write here? This is C1. So C1 is odd multiplication by 0. C2 is even multiplication by 1. So you see that for H0 everything is easy always. C0 over image of delta 1, which is 0. C0 is integers. So what we get is integers. Okay, that is the latter part of the proof. What is H1? It's kernel of delta 1 over image of delta 2. What is kernel of delta 1? Kernel of delta 1 is nothing but the entire ring of integers. As you see, for so this is 0. What about H2? So numerator is 0, so this becomes 0. So this is true for all odd cases. Yeah, take argument of H1 and extend it for all odd cases, and you can extend the second argument for all even cases. As you can see, if it is even, then you have an injective map, so kernel is 0. And if it is odd, it is multiplication by 0 map. So entire complex lies in the kernel. And that is pretty much it, the argument. So why reduced homology group? The reduced homology groups allow us to build general theory. And in fact, when you use categories and functors, or later on study generalized cohomology or homology theories, you will always encounter reduced homology groups. So they make life easy. They make proofs easy. And we will actually, in the evolution of the course, we will try to do something with reduced homology and other homology groups. The difference, in fact, what proofs I have seen, the difference is just in the last line of the sequence. But reduced homology groups make life much more easier. So what is reduced homology? So as I have mentioned before, we want for a point for all groups to be 0. So we just put a tilde over H to represent reduced homology. So let us write this down. So how do we do it? So you take our standard simplex or chain complex and append a ring of integers to the end of it. That is it. And the map is what? The map is just the same old map which we have been using. So you see this map is clearly onto. So what are the two important points we get from this? The first point is that for n greater than 0, there is essentially no difference because we have done nothing. But it is in the 0th group there is a difference which arises. H0 of x is nothing now but the reduced homology groups and direct sum with integers. Now as you can see, in this case now the point will be 0 because of the direct sum. You should also reach page 110 of Hatcher. So now we want to talk about homotopy invariance. So take two spaces x and y. These are homotopically equivalent if there exists map f from x to y and map g from y to x such that these two conditions are satisfied. So you take g, go to x, apply f, come back to y, you get idy, and similarly if you take f, go from x to y and then take g and come back to x, you get id on x. So the fundamental idea is this: homotopically equivalent spaces have isomorphic homology groups. So what are the examples? So if space x is contractible, then x is isomorphic to a point. So the reduced homology groups are 0. The second point is Mobius. Now this is an exercise in Hatcher, I think the first exercise of chapter 2. So Mobius is isomorphic to circle. So see, I've already started using reduced homology groups. So take a map f from x to y. This induces a map f hash from CNX chain complex x to chain complex y. Now how does this map come from? It's very easy. It's just obvious actually. So you apply sigma here, you apply f here. This is given to you. So this map is f hash. So what is it taking? It is taking sigma here and mapping it to, let us write it down here again. So this map acts linearly. So what does that mean? So as you know that we have to first write the free group f hash acts on this free group. So now I'm saying f hash is acting on CNX. Acting on CNX. So linearly means it jumps the coefficients and comes directly inside. So f hash is acting on CNX. So again, what does f hash of sigma is? Nothing but this. F naught of sigma I. That is it. Now why is this important? This we are going to use in, let us draw this important map which we will get. So we are drawing map between two chain complexes. This map has been induced by a homotopy map F. So we need to show that this diagram is commutative. So you start with left hand side, you are acting on the boundary, just write down the formula for the boundary, sigma acting on the simplex with ith vertex missing. Use linearity, bring f hash inside and say like take sigma I minus 1 raised to the power I outside. Yeah, now this obviously this looks precisely like the boundary of delta f hash, yeah, because f naught sigma inside is nothing but f hash, and so minus 1 raised to the power I sigma I is nothing but boundary of f hash. Yeah, that is pretty clear. You apply the boundary operator, what you get is inside the expression you have f0 sigma, which is acting on the simplex with ith vertex missing. Yeah, this is what we get by using boundary.